All right, so we're going to take a look at section 7.5, okay, which is going to continue what we started to learn about identities in section 7.4. So just a reminder of the identities from 7.4, in case you need those again. We learned those three groups, and we're going to be expanding on those with some different groups. Okay. The main groups you guys are going to learn today are called Sum and Difference and Double Angle. So two more groups to add. So first of all, I want you to look at those two things. The sine of x plus 3 compared to the sine of x plus the sine of 3. It's almost like they tried distributing the sign. So the question is, can you do that? Well, let's graph what's on the left in y1. And let's graph what's on the right in y2 and see, are they the same? Anybody have a guess before I hit graph if they're going to be the same or different? Same? Different? It's going to be one of those two. There's no further. So let's go zoom 7.
Neither show up.
Oh no, it'll show up. So there's sine of x plus 3. And I'd have to zoom in a little bit. It is a little bit off. It's because the plus 3 isn't, it's only a 3. That's not very much. But if I go zoom 2 and zoom in, I think you will see it a little better. Or I could have made the plus 3 like a plus 30. Then you really see it better. But can you see now that they're off? They're not exactly the same. They overlap in certain parts, but they are not exactly the same right on top of each other. So the point here is you can't do that. There is a way to deal with what happens when there's a plus inside here, but it's not distributing the sign. Okay, you can't do that. If you think about it from a transformation perspective, this is adding a number on the end. What kind of transformation is that? When you take a function and add something on the end of it, how does that move it? Yep. Not horizontal. This one is, yep, Jared? Vertical. Like if you had this, that would be the square root of x shifted up 3. When you add inside, that's horizontal. So just from transformations, these are two totally different things. This is a vertical shift. This is a horizontal shift. Specifically, this is a shift up. This is a shift to the left. Okay, so they're not the same. So what does work? Well, I'm going to show you. So we're going to learn what's called the sum and difference identities. And it's a formula that you can use when you have a sum or a difference inside the parentheses to simplify it. Right? And there's 6 formulas. We're going to look at the sign when you have a sum. We're going to look at the sign when you have a difference. We're going to look at when it's cosine with a sum, cosine with a difference, tangent sum, tangent difference. So there's 6 of them. The sine and cosines are the most important. Tangent's not as important. I'll give it to you so you have it, but we're really going to focus more on sine and cosine. So we're going to start out with the cosine difference formula. The proof of this is a little bit lengthy, so we don't go through it. It'll take about 15-20 minutes to explain where it comes from. But what we are going to do is, now that I gave you this one, we can use this one to figure out all the other ones very, very quickly. All right. So I'm just going to start you off with this one, though, because the proof, it just takes too long. So this is what we call the cosine difference formula. And alpha and beta could be any 2 things. Sometimes one of them will be a letter, one of them will be a number. Sometimes they'll both be numbers. Depends on the problem. But what I do is I usually call alpha, when I read that, first, and I call this one second. So the formula is cosine of the first times cosine of the second plus sine of the first times sine of the second. And you're going to hear me use the words grouped and mixed. Your book doesn't really use those, but I use them. I call this one grouped. I call it grouped because all the cosines are grouped together on one side. All the sines are grouped together on the other side. When I say mixed, it's going to mean you have a mixture of sines and cosines on each part. This one's not mixed. Cosines are all together, sines are all together. Okay, so this one is, they're grouped together. They're not mixed. Right, you'll see one that's mixed in a little bit. So again, the proof of that is on page 409. Not something we're going to go through. So what we're going to do is we're going to use that formula to figure out this problem. I want the exact value of cosine of 15 degrees. I don't want this. I don't want 0.965925826. That's not the exact. That's a decimal. So, up until now, the angles that you guys have worked with have always been that we can do exact answers for, have been multiples of 30 or 60. So if you want to think of all the angles that you guys have done so far, you've done 0, 90, 180, 270, and you've done a 30, 60, a 30, a 45, and a 60. And you can do the 30, 45, and 60 in every quadrant. 30, 45, 60. 30, 45, 60. Any one of those black dots, and there's 16 of them, we can do as an exact answer. They're all going to involve square roots of 3s, square roots of 2s, things like that. What we're learning how to do now is the angles that are missing, the gaps in here, the 15s. That's a 15, 75. So we're learning how to do the multiples of 15 and 75 in each quadrant. And now we have 1, 2, 3, 4, 5 different points we're going to be able to do in every quadrant. The red ones are the new ones. But to do the new ones, you use the old ones. The way you do this is you have to write 15 thinking of this idea. Something minus something. But it can't just be two random numbers. It can't be like 17 minus 2. 17 minus 2 is 15, but that won't work. Each of the numbers that you put here and here have to be multiples of 30 or 45. Because if you put numbers there that are multiples of 30 and 45, we know how to do those ones. So can anybody think of how you can write 15 as a difference of two numbers that are multiples of 30 and 45? Yeah?
45 minus 30.
Yeah, so this one is 45 minus 30. Now what you do is look at your formula. Alpha is 45, beta is 30. Just fill in 45 and 30 everywhere you see an alpha and a beta. So let's go through. Cosine of the first number times cosine of the second number. All right. So cosine of the first, cosine of the second. Plus. Okay. One thing you'll notice with the cosine formulas is whatever symbol you have here, it's the opposite there. When we get to the sine formulas, whatever symbol you have here is going to be the same here. Okay. But for cosine, it's a plus. All right, so we're going to have plus sine of the first, sine of the second. Sine of the first, sine of the second. So sine 45, sine 30. Okay, now we have 4 problems or 4 calculations we have to do there. Each one of those we have to write as an exact answer. But we're going to get numbers that we should recognize here. Let's start with cosine 45. That's not just a random decimal, that's a special one. 0.707. What is 0.707 as an exact fraction? Yep. Yep. So if we go back to our chart that I gave you guys, 0.707 is square root of 2 over 2. Okay, so we got that one. Times. Now we need cosine of 30. Cosine of 30, that's another special one, 0.866. Anyone remember from the chart what 0.866 is? Yeah. Square root of what?
3 over 2.
Yep. Plus, let's do sine 45. Again, I'm not looking for 0.707. We just did that one earlier, root 2 over 2. And the last one is the sine of 30, which is 1/2. Okay. So now we've got a calculation. Nothing in that is rounded. We're going to just simplify what we can and write our final answer. Okay. Square root of 2 times square root of 3 is the square root of what? Yeah.
6.
Square root of 6. So we're just going to put those together. So what I'm doing this part, and I'm doing this part. Brandon, 2 times 2 plus, what's my fraction going to be from the second one? You sure you want to go ahead?
If you're waiting for me.
Yeah, what would it be?
Square root of 2 over 2. Or 4.
4. Now we have two fractions, but what do you have to have if you want to add fractions together?
My denominator.
You got to have the same denominator. Do we have that here?
Yeah.
So we're fine. We can just put one big denominator. Square root of 6 plus square root of 2 over 4. That's as simple as you can get. So very easy to check. This was the cosine of 15. Let's type in what we just got and see if that's the same thing. Square root of 6 plus square root of 2, that's the top, and now divide that number by 4. It's exactly the same thing, 0.9659. So calculator won't give you the exact answer. This is the only way to get the exact answer for multiples of 15. Okay? So the key, again, split that number up so that it's two numbers. Each number has to be a multiple of 30 or 45. Any questions on that one? And once you guys learn the cosine sum formula, it gives you more options, because then there might be more than one way to do the same thing. If I give you a number that's a multiple of 15, some of you might be able to think about how to do it as a difference. And some of you might say, oh, I figured out two numbers that you can add to do it. So once you know it, you have more than one way to do the same thing. So this is a verify. So when you're asked to verify an identity, which side did I always suggest you start with?
Right.
Which one?
Right.
It's not really placement. You can't really say whether it's left or right. But you should always start with the side that, yeah, that's more complicated, whether that's the left or the right. In this case, it's the left. So our goal is going to be to take the left-hand side, do something to it, and when you're done, get sine. Now, look at what we've got. It's a cosine difference. It's this formula right here, where the first one is pi over 2, and the second one is theta. So everywhere you have an alpha, put pi over 2. Everywhere you have a beta, put theta, and write out exactly what's on the right-hand side. Now, only some of this is going to simplify. The stuff with numbers will simplify. The theta will not. That's your first. That's your second. All right, so let's start out with writing our formula. How does the cosine difference formula start? What's the first trig function? Yeah, Zach?
Cosine pi over 2.
Yep, cosine. And you know what? Let's just write it all out. So we have a cosine. What's the next trig function? Cosine. Plus or minus right here? Plus, and then the next two? Sine, sine. So that's what I usually do first. Cosine, cosine, sine, sine. And now fill them all in. Pi over 2, theta. Pi over 2, theta. 1, 2, 1, 2. Pi over 2, theta. Pi over 2, theta. So now we'll type in the ones that are numbers and see what happens. What's the, you type that in radians. What's the cosine of pi over 2? Yeah, 0. 0. I'm just going to write that below it. And what's the sine of pi over 2? Or another way to think about pi over 2, there's your graph of sine. Pi over 2 is a quarter of the way through the cycle. Where are you at when you're a quarter of the way through the cycle? 1. So I'm just going to cross that out because it became 0. I'll cross that out because it became a 1. What's 0 times cosine theta? 0. So this whole first part that I just put a box around, it's 0 times cosine. It just turns into 0. Okay? So all we have there is 0 plus 1 times sine. What's 1 times sine? Sine. And now just finish that up. What's 0 plus sine? Sine. So the left-hand side of this problem is sine, and the right-hand side was sine. So we verified that what's on the left is the same as what's on the right. So it's kind of like an identity from last week, but it's a lot easier because you have a formula. All you have to do is fill it in and simplify what you can. Usually with an example like this, everything turns into like zeros, ones, or negative ones. That's usually what has to happen to make it work. Okay, any questions on that? Right, so keep that in mind, because we're actually going to use that fact later on. The fact that the cosine of pi over 2 minus theta equals sine. It's not really another identity. I mean, it is an identity, but it's not one of the ones that we're going to like put in one of the categories. It's just another fact we figured out. But keep that in mind. Okay. Let's look at this one. They want you to prove that the cosine of pi minus theta is the same as negative cosine theta. Right. So first thing we want to try to identify is what identity that is. So when I'm asking you for a name there, I'm looking for you to tell me a trig function, and I'm looking for you to explain if it's a sum or difference. So what I circled on the left, what would be the name of that identity that we would use? Yeah?
Cosine difference.
That's a cosine difference problem. Cosine is the trig function, difference is the operation inside. Okay. So let's write down the formula for cosine difference. Nikira, when I write that, what comes first?
Cosine.
So cosine. What's the next one?
Cosine.
Cosine. The symbol we're going to put in between. Yep, when it's cosine, it's always the opposite. And Sam, what about my last two?
Sine.
Yep, and
Sine.
sine. So again, I call this grouped. Cosine's grouped on the left, sine grouped on the right. And Brianna, what's going to go in my first parenthesis? Pi. Caleb, second parenthesis?
Theta.
Theta. Third one, Emily? Pi. And the fourth one, theta. So the thetas don't simplify, but the pi's do. Let's just think about this one from the graph, okay? Because you'll be able to do it without a calculator. Pi is what in degrees?
180.
It's 180. How far of the way through a cycle is 180 for cosine? Yeah, it's half. So here's the graph of cosine. Here's your quarter points. 0, first quarter, second quarter, third quarter, fourth quarter, all the way down. Where are you at when you're halfway through the cycle? Emily? This is -1. Okay. Now for sine, you can do the same thing. Here's your graph of sine. Here's your quarter points. 1, 2, 3, 4. Sine of pi is halfway through the sine cycle. Where are you at when you're halfway through sine? Yeah, 0. Let's cross that out. And Eric, what's -1 times cosine? Negative cosine plus. Chris, what's 0 times sine? 0. Negative cosine plus 0 is negative cosine. So we just proved that the left-hand side is negative cosine. That's exactly what was on the right. On the test, you'll probably have 2 problems just like that. I'll give you something on the left and have you prove that it's what's on the right. Okay, so there's your cosine difference. Now let's take a look at the cosine sum. So I didn't prove to you where the first formula came from. Okay, I told you that one takes a while to prove. But once you have that one, the other ones are easy. So 2 things I have to remind you of in this one. What's the difference between the answer that I just got there and the answer that I got when I did that one? Nothing. When you have a negative inside a cosine function, the negative doesn't make a difference. It doesn't matter at all. So whether you put the negative in there, you leave the negative out, those 2 things are the same. Now let's try that with sine. Let's do like sine of 30 and sine of -30. Are those 2 things the same?
No.
What's the difference?
Negative.
One of them's negative. So this time the negative is important. But what you can do is that. If you have a negative inside, if you want, you can just put it in front and you'll get exactly the same answer. So with a sine, you can't get rid of the negative like you can with cosine, but you can take the negative and move it to the front. Those are 2 special things that happen with sine and cosine. Now, we're ready to figure out the cosine sum formula. So you got cosine difference. Now we're going to do cosine sum. Now, The only formula you guys know right now is cosine difference. So somehow you have to turn that into a difference. If you can turn that into a difference, then you can do it with what you already know how to do. Anybody tell me how you could write alpha plus beta as a difference rather than a sum? Yeah?
Negative alpha plus negative beta, or minus negative beta.
All right, can you say it one more time? You're on the right track.
Negative alpha minus negative beta.
Not quite. Yep.
You just flip the sign on the other side.
So what would you put here?
Beta.
Doesn't it? You don't have to change the order. So like, how could you write 3 plus 2 as subtraction and get the same answer? Let me pretend your plus button's broken on the calculator. I want to type that in, and I want to get 5 somehow. So you got to get 5. Yep.
3 minus negative 2.
3 minus negative 2. So do you see what you do here now? What would you do?
Alpha minus negative beta.
Alpha minus negative beta. So there's your first. There's your second. The first thing is what comes before the minus. The second thing is what comes after the minus. Comes after it. Now, fill all that into the formula you have for cosine of a difference. Simplify it, and when you're done, now you'll have cosine of a sum. And you won't ever have to do this again, because then you'll have a formula. All right, so we've got cosine, cosine, minus sine, sine. First, second, first, second. First, second, first. Forgot my translation. That's sine. Okay. Now, the ones that don't have negatives, we can't really do much with it. So this stays the same. What about cosine negative beta? What's cosine negative beta the same as?
Cosine beta.
You can just get rid of the negative. Let me just check. I think we're pretty good. I think I just messed up one of the signs. So when it's a minus, I should write a plus. What did I do? When it's a minus, I should have written plus. So luckily we caught it before we got really far into it. Okay, so we've got cosine alpha, cosine beta. We can just get rid of the negative. Sine alpha. That part's going to stay the same. How about the negative on the beta in the sine? Can I get rid of the negative?
No, we move it.
No, where can I move it?
The left.
Yeah, I can put it in front. I can put it right there. So instead of saying sine negative beta, you can put the negative in front. So here's your formula for cosine of a sum. It's almost the same formula. Cosine, cosines grouped on the left. Sine, sines grouped on the right. But notice, when it's a plus, you put a minus. That's why I think the reference sheet is helpful, because all these formulas are kind of the same. They all look something like that. So it gets a little tricky if you can't remember which one is which. So, sine of a sum would allow you to do a problem like this. Now, when I first look at the number 75, I can think of how to write that as a sum. But some of you might think of how to do that as a difference. So you might be able to do this problem with the first formula I showed you. You'll get the same answer. But I want to try it as a sum. Anyone think of how to write the number 75 so it's something plus something? And the two numbers have to be multiples of 30 and 45.
30 plus 45?
Yeah. Now that's how I'm going to do it. But can anybody think of how to write 75 as a difference? Think of two numbers that are multiples of 30 and 45. So one of your numbers is going to end in a 5. Yep. Think you got it, Tim? Yeah.
No.
120 minus 45.
120 minus 45. Yep, that's not the one I was thinking of, but yes, that would work. I was thinking of 135 minus 60. That would work too. So, lots of ways to do this problem. But we're going to just try it as a sum. Okay. With the cosine formula, are my trig functions grouped or are they mixed? They're grouped. Cosines are grouped on one side, sines are grouped on the other. So, cosine, cosine, sine, sine. We've got a plus, so what do we put down here? Yeah. No. Minus. We put a minus. And Eric, what's going to go right here? 30. Brandon, the next one. 45. You just follow that. 30, 45. Okay. Each one of those is going to come out to a nice number. Or maybe not a nice number, but a number you should recognize. Cosine 30. Nikira, what's 0.866? Brandon?
Square root 3.
Yep. So you just use that chart. Square root 3/2. How about cosine 45? We did that earlier. Anyone remember what that came out to? Yep. Yep. Sine of 30. Actually, we did all of these earlier. What's sine of 30? You remember that one? That was a half. And the sine of 45 came out to. So, yep.
Square root 2/2.
Yep. So all these problems have like square roots of 2, square roots of 6s over 4, square root plus, minus. They all kind of look something like that. So this one is square root of 6 minus square root of 2 over 4. Where the one we did the first time I think was a plus. This one was a minus. Okay. And if you found cosine 75 using any of the other ways, you'd get the same answer if you did everything right. So in general, if I give you a problem like this on a test, I don't care which way you do it. Do it as a sum, do it as a difference. I'm not usually going to say which way you have to do it. Okay, let's take a look at the sine sum formula. Now, for the sine sum formula, I want you to look at it and see if you notice something, a couple things different right away. It's going to look similar, but if you look closely, it's not the same. So we just finished the cosine group. Now we're looking at the sine group. Anybody notice something that's different in the layout of the formula this time? Yeah, this is what I call mixed. The sines aren't together and the cosines aren't together. That's what we did before. This is mixed. Sine, cosine, cosine, sine. Now, it's still first, second, first, second. That didn't change. But does anybody notice one other thing that is different? Yep.
the same sign in the middle.
Yeah. If it's a plus here, it's a plus here. With cosine, you have to make it the opposite. Okay, so that's the sine sum. Now, based on when we did cosine sum and difference, anyone think they could tell me the sine difference now that you know the sine sum? Or maybe just tell me what would change in that formula to make it the sine difference. Yeah.
Sign. Like the value sign.
What would it change to?
Negative.
Yeah, the plus is going to go to a minus. So there's your sine difference. Still mixed. Sine, cosine, cosine, sine. First, second, first, second. Minus here matches the minus there. Right. And now with that, you could do a problem like sine 15 or sine 75, just like you did cosine 15 and cosine 75. It'd be pretty much the exact same thing. So rather than go through a whole problem, I just want to practice if you guys can figure out how to take a number that's a multiple of 15 and write it as a sum or difference. Let's try 165. That is a multiple of 15. So if I asked you for the sine or the cosine of it, your first step would be to split it up as a sum or difference. Can anybody think of how to write 165 as a sum or difference of two numbers that are multiples of 30 and 45?
Thought I had.
Yep, there you go. So that's one way that you could do it as a sum. 120 plus 45. Anybody think how you could do it as a difference? And I don't mean 120 minus 45. How could you write 165 as a difference? Yeah, that doesn't count. So that's really just taking this one. I mean, technically, yes, but how about as a difference with the other numbers besides 120 and 40? Yeah. 15 is not a multiple of 30 or 45. So you gotta pick numbers that are multiples of those two.
10 minus 45.
Okay, yep. 210 minus 45, let's check. So 210 minus 45, perfect. That's not the one I was thinking of. I was thinking of 225 minus 60. 225 is a multiple and 60 is a multiple of 30. So if you've got to work with the number 165, those are all different ways you could break it up. Just takes practice, I guess, to get good at breaking it up. All right, I'm going to give you the sum and difference identities for tangent. So now you'd be able to do a problem like tangent of 15, tangent 75. But even before I give you this problem, could anyone think, with what I've taught you so far, and something we learned in section 7.4, how could you do the tangent of 15 before I even give you the formula for it? Think of what's another way you can write tangent besides using tangent. Yeah? So technically, to figure this out, this would be a very long way to do it, but you could do that. You could do the sine of 15 first, do the cosine of 15 second, get those two answers, and divide. So you could figure out tangent without the formula I'm about to show. But there is a formula for tangent, and that's the formula for tangent of a sum. Okay, at this point, they start to get really weird and kind of hard to remember. So it's tangent first plus tangent second over 1 minus tangent first, tangent second. And the difference formula is pretty much the same, except all the positives and negatives change. So now we've got tangent first minus tangent second in the top, and 1 plus tangent first, tangent second in the bottom. Again, I don't know how you'd be able to keep all that straight. You might be able to remember part of the formula, but then you'd probably mix up the pluses and the minuses because they're almost the same. Okay, so if I give you a problem with a tangent, it would not be a verify. Okay, sine and cosine on the test, definitely going to give you problems like that, and I'm going to give you problems like that. For tangent, I would only give you a problem like that. Find the tangent of 75. Find the tangent of 165. Okay, something like that. Now, when you deal with tangents, if we go back just a second for this one, you guys split up 165 into 120 and 45. So, if I was finding the tangent of 165, that's one way you guys told me I could do it. Well, when you take the tangent of the first, tangent 120, you get negative 1.73. That's a special number we talked about. So if you go back somewhere, right here, negative 1.73, negative square root of 3. So when you do this problem, these are going to come up. When you do the problems we did at first, we were dealing with sines and cosines. These came up. Sines and cosines, you're going to see numbers on the left. Tangents, you're going to see numbers that are on the right. Square root of 3, square root of 3 over 3. Okay. Any questions on those two identities? Okay, so the last thing in this section. When you have a number inside the parentheses in front of your variable, and you want to get rid of that number, you can't just put the number in front. That doesn't work. Let's graph it and see what happens. So let's do sine 2x and 2 sine x. This time, you'll be able to see this very clearly on a standard window. I'm not going to have to zoom in. These aren't even going to look close at all. Totally. So, the first one is a period change. You have a big number inside next to the x. Big numbers compress your graph. They shrink it. So that 2 is actually shrinking the graph by a factor of 2. On the right, that 2 is in front. That's a vertical stretch. Multiply by a number in front, it stretches it out to be twice as tall. So, point here is they're not the same at all. So then how do you deal with 2? Right? We know how to deal with a sum, we know how to deal with a difference. How do you deal with it if it's a 2? That's how you deal with it. And I'm going to show you, not for all of them, but just for this first one, why this turns into that. sine 2x would be equal to 2 sine cosine. And that I can graph. Let me graph it first just to kind of show you they look the same. So sine 2x and 2 sine cosine. So what I did is I just typed in example 4. Okay, it's a graph. There's sine 2x, you guys just saw that. And now watch 2 sine cosine. Same thing. Now, a picture doesn't prove anything. Who knows, maybe you zoom in more and they're not the same thing. Right? But in this case, they really are. So what we're going to do is we're going to prove that what's on the left is the same as what's on the right. I'm going to start with the left-hand side and focus on that, 2 theta. Can somebody tell me arithmetic you could do like this, and the answer would be 2 theta, besides 2 times theta. 2 times theta is 2 theta. But what other simple arithmetic could you do and get an answer of 2 theta? Or think of like 2x. Like in algebra, how could you get an answer of 2x? If you did this and this, the answer could be 2x, besides 2 times x. Something simple, yeah?
4 theta divided by 2.
Okay, you could, even simpler than that though. Yep.
Theta plus theta.
Theta plus theta. Theta plus theta is 2 theta. So let's think of the left-hand side like that. That's the left-hand side, theta plus theta. That's a sine-sum identity. I just taught you guys that identity. This is the first. This is the second. The first and the second are the same. So let's see if we can write it out. Okay, with a sine identity, what symbol am I going to put in the middle? A plus or a minus? Plus, it stays the same. Are the trig functions grouped or mixed with a sign? They're what? Mixed. So that's a sine, cosine, cosine, sine. They're mixed. Sines and cosines are mixed together on each side. First, second, first, second. Theta is my first. Theta is my second. Theta is my first. Theta is my second. Now, look at what's on the left of the plus sign. Sine times cosine. Look at what's on the right. Cosine times sine. Is there a difference between sine times cosine and cosine times sine? No, it's like saying 5 times 8, 8 times 5. So you have a sine times a cosine plus another sine times cosine. How many of them do you have? Remember? 2. You have 2 of the sine times cosines. 2 of those things in parentheses, which is exactly what's on the right hand side. That's why sine 2 theta equals 2 sine cosine. Okay, so the last group of identities I'm going to give you guys are called double angle identities. They're called double angle identities because they're all identities that have a 2 next to the x. Okay. Or the theta, whatever the variable is. Okay, so there's your first one. Sine 2 theta. Now, before we look at the next one, which is for cosine 2 theta, I'm going to go back and look at something that I showed you guys from section 7.4. I want to go back and look, just for a second, at a Pythagorean identity. Specifically this one. Sine squared plus cosine squared equals 1. I'm going to just copy that to what we're doing right now. Just up here for a second. I'll come back to that. There's your formula for cosine 2 theta. Looks nothing like sine 2 theta. Totally different looking. It's cosine squared theta minus sine squared theta. Or at least that's one way to write it. Now, I want to take my Pythagorean identity, which I wrote up here, and I want to get this by itself. If I wanted to do that, what would I subtract from each side? Yeah.
Sine squared theta.
Sine squared theta. So does everyone agree that cosine squared equals 1 minus sine squared? Anyone think that's wrong? Okay. So now, take that and fill it in right here. Don't erase what you have, because this is correct. I want you to have cosine squared minus sine squared. That's the first one. That's important. But we can make a second one. Change cosine squared to 1 minus sine squared. So if you put 1 minus sine squared in the thing that I just circled, you'd have 1 minus sine squared minus sine squared. What would that simplify to? 1 minus sine squared minus another sine squared.
2 sine squared.
1 minus sine squared minus sine squared.
1 minus 2 sine squared.
1 minus 2 sine squared. That's a different way of saying exactly the same thing, just using a Pythagorean substitution. Now, if you can substitute for what I circled here, then you could substitute for what I just circled there. You could have done that one. If you did it that way, you'd get something like that. Still using a Pythagorean identity and just substituting for the last part. All right, so there's 3 different ways to do cosine 2 theta. And the last formula I'll give you is the one for tangent of 2 theta. Again, most of the time I'm giving you the tangent one just so you have it. So if you ever have to look back at your notes, you're not really missing anything. But it's not one that we're going to focus on in this class. But if in college, if you have to go on and take like another math class after this one, like a calculus or something, they're definitely going to use tangent ones. Okay. So I'll show you guys a problem with those, but that's the last for the identities that you're going to learn today. So you got your sum and difference identities, just learned 6 of them. You got your double angle identities, sine 2 theta, cosine 2 theta, tangent 2 theta. So you just learned 3 of them. And now you got all these identities we learned in the last section. So now you have 5 categories of identities. But nothing you have to memorize, because you can make a reference sheet, which is very, very helpful for this stuff. Okay. So last problem. They're asking us to write 2 cosine x plus sine 2x using only sine x and cosine x. So basically what they're saying to do is when you're done, they don't want 2's next to the x anymore. Just x's, no 2 x's. So let's look at this one. The first thing that I just circled, is there a 2 in front of the x? Emily? No. What number is in front of the x? 1. That's fine. So the 2 cosine x1, you don't have to change anything with that. X already has just a 1 in front of it. There's a 2 on the outside, but they don't care about that at all. They just care about what's right next to the x. Now, this one is no good. We have to fix it. So what can I change what I just underlined 2. So there's no longer a 2 in front of the x. What's the formula we can substitute in for sine 2x? Brianna? Why did I call you? I'm sorry. And I'm just going to use I letters. So 2 sine cosine. So we just converted this so it no longer had a 2 in front of the x. Okay. So when you look at what I have in red right there, how many terms are there in that expression in red? I'm using a kind of a technical word, a term. How many terms are there? Yep, there are 2. Terms are separated by addition and subtraction signs. So there are 2 terms. 2 cosine x is the first one. 2 sine x cosine x is the second one.
How did you get the 2 sine x and cosine x?
From right there.
Oh,
Now, look at what I underlined in each term. What does the first term and the second term have in common? Yep. 2 cosine x. Whenever 2 terms have the same thing in common, you can factor it out and write it a little more simply. So let's write 2 cosine x. If you factor 2 cosine x out of this, what's left? You can't put a 0 here, that wouldn't work. Because then if you distribute it, you wouldn't get that back. Yep, 1. If you factor everything out of a term, the only thing left is a 1. And what if you factor 2 cosine x out of the second term? What's left there? Yep, sine x. Both the answer in red and the answer in green are correct. They're the same answer. And the directions technically just said, make sure you write it with just sines and cosines. No 2's in front of the x's. Well, if I look at the one in red, there's no 2's in front of the x's. If I look at the one in green, there's no 2's. This one is just a little more simplified. But technically, if those were the directions on the test, I would accept either one of those. If I said, do that and factor out anything that both terms have in common, then I'd be looking for what I just checked off. Okay. So any questions on that? All right, so like I said, I had given us 2 days for section 7.5, and we still have 11 minutes to spare, so I don't really think we have to rush through that too much. So what that's going to allow us to do is 7.6 is a little bit longer of a section. We might spend 2 days on that. And then Thursday is the easiest section. Okay, so Wednesday, 7.6 is the hardest. But 8.1 is very, very easy. So we might spend 2 days on that. We'll see. Okay, so homework is on page 417. Notice for number 31, I don't want you to do the whole problem. I think it has multiple parts. Just do part of it. So we'll take a look at that tomorrow, and then we'll spend as much time as we need to on section 7.6.